First thing I want to look at is the result of that very first set of arrows. You didn't show any arrows, or no arrows were shown to the OCH3, so you could go through and show OCH3. And the people that I looked at did that. That was fantastic. Okay. Then what I saw was the oxygen connected to the hydrogen, which is good. Okay. I'm being selective in my vision. I haven't finished the structure. Okay. And I think I even saw this guy out there, which was also good. Okay. The next issue comes in with what's happening in that gap. What I saw a lot of people have would be this. Okay. So if we ignore the issue with lone pairs, what is the problem with showing what we've got drawn there? What do you mean? There's an implied hydrogen.
No, we had a pi bond.
There is always an implied hydrogen unless you have specified a charge. Should a hydrogen have been added there? No. So by drawing it that way, you have now implied something incorrect. That's going to ruin every other step of the mechanism. Because you now know, or you in theory know, that this oxygen has to somehow react there. And you're like, well, how can it react? It can't react. It would exceed its octet. You're right. That would be a problem. It would exceed its octet. Because what you've got shown prevents you from doing that attack. Okay? This is why it's really important to draw out your arrows carefully and draw exactly what they're saying happens. Okay? So that hydrogen should not be there. So then I got people saying, well, it's a carbocation. Well, what did I just say about showing what your arrows show?
You didn't show the carbocation.
Okay. Nothing about the arrows shown suggests the formation of a carbocation. Absolutely none of it. Okay. I know why you want to do that, and we'll have that discussion here in just a second. Okay. But your arrows do not show that. That means you should still have the pi bond. One of the lone pairs is still there. The other lone pair went into making that bond to the hydrogen. We would now have a positive oxygen. That's what your arrows show. Okay? So let's go through to breaking the pi bond. Okay? What you're trying to do, or what you were attempting to do, would be this reaction, which I'm going to delete here in a second. What you were trying to get to was this, okay, which is fantastic. That's really good because we can see an electrophile. We can see that reactivity, and I appreciate that. Okay? However, that is not what the arrows showed. Okay? So if that's what I want to get to, fine, I'm okay to show that. Don't forget the positive charge. Okay? And so what you've done is memorize what you want to get to and then just hope the arrows work themselves out. If that's what you got to do, that's what you got to do. The whole point of arrow pushing is so that you don't have to memorize. You follow how the arrows work. Okay? So let's double back to that starting stuff and say, well, what arrows would I need to have seen to draw that resulting structure? Nope. Resonance doesn't necessarily have anything to do with this yet. What arrows do I need to add to the nice, pretty structure in black to make the structure in blue? It's not going from the double bond to the oxygen. Where's that double bond going? If I was to draw a mechanism, is that a valid mechanistic step? Am I allowed to do that?
Yes.
Your answer should be emphatically yes, because of first semester and because of the first unit of this semester. Okay? The problem with that potential arrow is you don't necessarily know where the hydrogen went. The way we know where the hydrogen went is for a variety of reasons. One, we could say Markovnikov's rule. Decided I didn't want to worry about it and I just memorized it. Okay. Two, I recognized that if I placed the hydrogen at the other position, there were two places it could have gone. The blue one was awful. The purple one makes more sense, right? Because I form a more stable carbocation. I don't have to show resonance of the alkene, and in fact, arguably, I should not. I show directly the pi bond attacking the hydrogen. Okay? The result is that I am missing an octet, and that is a bad structure, okay, which is going to become the issue we're going to see with our carbonyl here in a second. Okay? That is a bad structure, but I don't have a choice. That is the only mechanistic step I can show. Even if I go through and show resonance, I'm going to show the loss of an octet. Okay? So because of that, I use the minimum amount of arrows to get to my point. Make sense? If we go back up to our carbonyl structures. Okay, we've got our blue arrow. Whoops, I haven't drawn the blue arrow yet. That pi bond is now going where? Where are those electrons going? They're not going to the oxygen, because if they went to the oxygen would have another lone pair. And in our product, it does not. Where's that pi bond going?
The oxygen does have two pairs.
It has two lone pairs. If we were saying that pi bond, that purple, went to the oxygen, how many lone pairs would it have?
But for that,
It would have 3. If we also say, well, one of those lone pairs connects to the hydrogen, which is what you might be saying, you're now showing 2 arrows. Go back to the alkene. What you're saying is that this should be electrons going to the carbon and then going to the hydrogen. When we look at the alkene, is the blue set of arrows correct? No. It's hands down wrong. And if you tried to provide that, you would get it wrong. The same thing's going to happen with the carbonyl. Where's the pi bond going?
but for that step, we wouldn't show the arrows. You show it after you had.
The red arrows are invalid. You're right. That's why I'm showing a blue structure here. I want to add arrows to the nice, pretty structure, okay, to get this blue product. The pi bond's going straight to the hydrogen. That's it. That is all it shows. Okay? And a lot of people freak out and go, oh my God, you can't do that. You did that with an alkene. It's the exact same process. How do we know that that pi bond is going to be shifting the electrons to be in a bond between the oxygen and the hydrogen and not the carbon and the hydrogen? Oxygen is more electronegative than the carbon. The electrons are going to shift towards the oxygen side of that when it makes the bond with the hydrogen. It's implied in that entire process. Okay? So now the question's going to come out, which should we be doing? Should we be showing the blue arrow, which officially, yes, we'd still have to break that one. Okay? Should we be showing the arrows for the blue, or should we show the arrows for the red? Okay?
Depends on how many steps more red.
It's not even dependent on how many steps you want to go through and do, because it's going to be the exact same number of steps. We're going to show the arrows for the red one, not for the blue one. Okay? And this is where I would argue we can run into an issue here. The issue that I see is that which is higher in energy, a pi bond or a lone pair? What orbital holds the lone pair? All the way back to OChem 1. It's a hybridized orbital. In this case, it's an sp2. What orbital holds the pi bond?
P.
A p orbital. Which is higher in energy, p or sp2? P. Which bond should you break? You should be breaking the pi bond. However, the result of using the pi electrons results in a structure that is missing an octet. The result of showing the lone pairs results in a structure that does not miss an octet. When we go through to draw mechanisms, we want to use the fewest arrows to get us to the most stable structure. What is the relationship between the black structure and my crappily drawn black product? They're resonance structures. They are identical to each other, except the blue one is worse than the black one because of octets. What does that mean? When being asked to draw a mechanism, you don't show the formation of the carbocation. Okay? We've talked about the formation of the carbocation and using that to help us predict the reactivity, okay? Which goes back to what we've talked about in first semester for like 3 of you, 4 of you, okay? And the rest of you may have missed. When we're trying to determine reactivity or structure drawing, we always draw the best Lewis structure. Okay? But if I want to know something about its reactivity, I don't look at the best Lewis structure, because the best Lewis structure is the most stable. So it's not going to react. What should I be looking at? The first worst resonance structure. Okay? The second best. That second best resonance structure gives me an idea of the reactivity. The reactivity on that carbon is that it's positive and it wants electrons. Kind of makes sense? Can I still show that reactivity from the black structure? Can I still get to what was the blue structure?
Yes.
Yeah. What did we say the relationship was? Their resonance. That's fair game. I'm allowed to do that. Yes?
Isn't there, from the second oxygen, isn't there another resonance system there? Isn't that?
There's another resonance system that you could try and throw into that, which arguably is probably better than what Carty's showing here, but what Carty's showing here is the sociocultural norm in organic chemistry, which means this is how you have to draw it. Whether you like, I know what you're saying. This is how you have to draw it. Yes, you can show that oxygen contributing in and having the pi bond electrons come out.
We're talking along the lines of like, isn't the, when putting the positive on the other oxygen, no, that's more stable, isn't it?
Yeah,
More
octets.
stable. Because of
Octets.
and everything.
Yep. Okay. So now we've identified reactivity. So what should we do? React it. We found a positive charge. What does it need? It needs a nucleophile. It needs electrons. Where are those electrons? Lone pairs on that alcohol that we just formed. Those electrons could come in. Because I've already added arrows to the carbonyl structure, I can't have the alcohol attack that, because now I'd be showing 2 sets of arrows doing 2 different things. So I would have to show it attacking the resonance. Okay? Realistically, or in an ideal mechanistic sense, should I be having the oxygen attack the resonance structure, that blue one?
No.
Why not? The blue one is the least stable. It shouldn't be involved in the mechanism. It's there to explain something about its stability and reactivity, but we shouldn't actually be using it as a core step in the mechanism, okay, to be fully correct. Okay, so now what is the result of that?
Your tetrahedral intermediate with positive oxygen in the alcohol.
We now have our tetrahedral intermediate. It's not a CH3, it's that stupid long chain. So 5. And then we'd have a positive charge on that oxygen. Does oxygen want to be positive? No. So what do I need to do? I need to deprotonate it. What do I deprotonate it with? Anything remotely basic. Okay? So the easiest answer to do for this kind of mechanistic step is just to say B. Not B minus, because B minus is strong base. What is the result? We've now picked up that lone pair. There's our 5 OCH3. Now what do you want to do? Reform the pi bond. We have the pi bond come down. We would exceed the octet, so what do we do? Kick out our leaving group. What's our leaving group? We want OCH3 to be our leaving group, which looks like 5. I apologize. Okay. We want that to be the leaving group. Is that any better or worse than the other structure, the other leaving group? No. Which would mean both are equally likely, which means we aren't really going anywhere productive. Okay? Are either of them good leaving groups?
No.
No. Why not?
Negative. It's an acid.
It's acid-catalyzed. I'd be kicking out a negative charge. Can I have a negative charge?
No.
No. So that's bad. I can't reform the pi bond. What did I just undo?
You have an acid. Can't you put on an H plus, like, and then?
I am in acidic conditions.
Okay.
I could put on the hydrogen. O 5 OCH3H. That would be positive. Now what could I do?
Now you can reform the pi bond. And
Now I could reform the pi bond, kick out the leaving group, and now I would have the final product, right?
no, because then you have, whoa, you missed an oxygen, hydrogen.
I'm going to deal with that in a second.
Okay.
In the formation of that pi bond, I've done nothing with that hydrogen, which means that oxygen is positively charged. So what has to happen? Something remotely basic can come through and deprotonate that. That gets us to our final product, which I'm just going to write FP. Okay? So if we look at this mechanistically, we've got 1, 2, 3, 4, 5, 6 steps. If we ran under basic conditions, we were probably doing it in 2. Okay? So acidic conditions catapult the number of mechanistic steps. Does that make sense?
Why couldn't your acid protonate the alcohol? Is that possible?
Why couldn't the acid, are you saying kind of in this step here?
Yeah.
Yes, it can.
And can it do both oxygens or all three?
Would it do all 3 oxygens? All 3 oxygens can be protonated. If we protonate the OH, that would be a good leaving group. What do we end up forming? Water could leave. What's going to stabilize the carbocation?
Nothing. It's gonna
Nothing. So that's not going to lead anywhere productive. Okay. If we protonated the 5 chain, yes, that takes us backwards. Which brings up an interesting point. What you're saying is that this step is reversible. Which of these steps is reversible? All of them are reversible. This is an equilibrium reaction. Transesterifications are heavily equilibrium dependent. Whoops, I just doubled that arrow. How can we ensure or attempt to improve the yield of our final product?
dump a boatload of reactants in.
Boatload of reactants doesn't necessarily improve the yield. You need to be a little bit more specific than that.
Play around with reactant concentrations so that you shift the equilibrium.
Reactant. One of the reactants needs to be increased. Okay? It is typically the alcohol. It could be the ester. Either one. Why is it typically the alcohol?
Alcohol
It's cheaper. It's also probably not the thing you're trying to make. you were probably trying to make an ester. Okay? So if you were trying to make the ester, where are you going to get a boatload of that starting material? That just doesn't make sense. Okay, so the alcohol is typically really, really cheap. It doubles as the solvent. Okay, so it can really help that out. What else could we do?
We could figure out whether it's exo or endothermic.
We
Take
could
that product, then
try and
form-
play around with endo or exothermic. We can try and remove product as it's formed. Okay? If we did this with water in the formation of a carboxylic, in the formation of an ester from a carboxylic acid, right, in that case we could remove water. The other product that's formed here is another alcohol. Can I remove that alcohol? Probably not, because it has very similar intermolecular forces to
Water.
the alcohol I put in to begin with. I begin and end with an alcohol. So it's not going to be easy to adjust the product concentrations except just remove the product altogether. Even then, is that going to be easy? You started with an ester and you end with an ester. Their intermolecular forces are going to be very similar. You're not going to be able to take advantage of a lot of stuff there either. Okay? So you're really just pushing by putting in the starting alcohol in a vast excess and hoping for the best yield you can get. Yes?
Can't you, because you're leaving alcohol here as methanol, which is water soluble, and if you've got a long enough.
So, and it depends on the ester. So what you're starting to suggest is now a nuance of what specific things are being placed.
But like,
That makes it way too over-detailed and wrong direction. Could you take advantage of intermolecular forces if your things were significantly different? Yes. Alcohol, alcohol. Keep it simple first.
even though the long carbon chain doesn't set that off?
Alcohol, alcohol. Keep it simple first. Okay? If a particular question scales that differently, you can look at the nuances of that particular question. Okay? That's asking a lot of any student. Any student. It doesn't make sense to go to that level of detail. Okay? So, that's our mechanism for our acid-catalyzed transesterification. Okay, so let's go ahead and swing it up and make it different. Let's look at this guy. Another named reaction. Okay. Have we seen this kind of before? Like, let's say if we just had Br2 and hydroxide. Make some subtle changes here. What might we have expected to see?
2 BRs on that.
Okay. This would be the haloform test, right? Under those basic conditions, this could go through and pull off hydrogens and do substitutions, putting on bromines up the yin-yang. Okay. What if I only wanted to put on one bromine? What could I do? Change it to acidic conditions. Whoops, didn't mean to erase that. Under acidic conditions, I only do one. Okay, so that could be helpful. Okay, what is different in the case of the Hell-Volhard-Zelinsky reaction? Okay, are we under acidic conditions?
Yes.
Yes. How do you know that? We have a carboxylic acid, so it is acidic conditions. Okay. The only place we would expect that substitution is at the alpha position, where there's alpha hydrogens. Okay? So how about I just add Br2 and a carboxylic acid? Shouldn't I get that bromination? Okay? And it turns out that that reaction doesn't happen. If I want that reaction to happen, what I need to go through and do is add PCl3. Okay? Technically, I also have to add H2O. H2O acts as what? Potentially as an acid or a base. Okay? Its reactivity is a little bit odd, so we won't stress about that. Why would that be important? Well, if our carboxylic acid acts as an acid to activate the whole reaction, what happens to that hydrogen? It would leave. So what would I need to do? Put it back on eventually. Okay? So the logistics of how we get that back on, we haven't fully addressed. Okay? So why do I need PCl3? Why does that have to get added in here? Right? So if we change this out back to our old haloform test, if we were haloform, shouldn't I be able to just do Br2 and H plus and get my substitution? Okay. Why, in the case of the Hell-Volhard-Zelinsky, does that not work? Why do I have to add PCl3? What was the first step in our haloform?
You're using the ketones.
So noticing key differences. We're starting with a ketone versus a carboxylic acid. Okay, that's an important note. Okay, that starting material causes a change in the reactivity that's going to become important. Okay, what we want to do is identify where is that key crux reactivity. Okay, and just saying that it's an acid versus not an acid isn't unfortunately going to be helpful. Okay, what was our first step in the standard haloform kind of reaction? David.
Activating the carbonyl.
Activating the carbonyl by reacting it with the acid so that what could happen? Oops.
So that you can then make the, you do the deprotonation on the alpha hydrogen, or you deprotonate one of the alpha carbons.
We could see that those alpha hydrogens become acidic because they're trying to stabilize that carbocation. So we could deprotonate that. Protonating the ketone increased the acidity of that hydrogen. What does this end up making?
Enol.
This whole reaction relies on the formation of the enol. I have to have that alpha hydrogen be reactive. Do I have an alpha hydrogen in the carboxylic acid?
Yes.
Yeah.
Yeah. So where's the issue?
If you pull off your alpha hydrogen, your acidic hydrogen next to the carbonyl.
What happens when we remove that acidic hydrogen?
Resonance stabilization.
We get resonance stabilization of what?
Carbon.
The carbonyl, which means
It's
the alpha hydrogens are
Less acidic.
no longer acidic, which means you can't enolize. Okay? So the acid doesn't work in the haloform condition. We can't do that enolization because the carboxylate does resonance stabilization that prevents the alpha hydrogens from reacting. Okay? That's kind of crazy. Big steps. Okay, so what is the point of PCl3?
Replace
to
the
stop that resonance somehow.
To stop that resonance somehow. Okay, yes, that's a good conclusion to draw. Or are you, Alex, you got a step above that? What did you say?
You substitute the OH.
PCl3 was used way back in chapter 10 to convert OHs into
CL3s.
CLs. Okay? For those of you who want to call me out on it, yes, I'm showing the incorrect chemistry, but it's close enough. Okay? That structure is now not a carboxylic acid. Okay? It's also not a ketone, though. Okay? Is that structure, does it have alpha enolizable hydrogens? Why now?
Resonance is tied up to the
That's what I was going to say. There's no resonance stabilization. That would make
The chloride is much less likely to actually share those electrons in because we end up forming a positive charge on the chloride. All of our halogens have a withdrawing effect. This is one of the reasons why the acyl chloride was so high in reactivity. If anything, we made the alpha hydrogens more acidic by converting it across to the acyl chloride. So what does that mean can now happen?
you can.
We can protonate, we can deprotonate. I lost track of all my carbons. We can form, whoops, because we had that hydrogen. Hey, look at that. It's like I knew it was supposed to be there. Okay. We now have that enolate or that enol that could now go through and react with the Br2 to put on the bromine. Okay. So you remember how we said, well, water, if our acid was going to act as an acid, we'd lose that hydrogen. We need to replace it, put it back on. That's why we had water. I have a chlorine. I don't have an oxygen to protonate anymore. So what the hell's the point of the water?
It's a nucleophile.
Water is going to act as a nucleophile to react with the acyl chloride to eject the chloride, leaving me with the final substitution. That's kind of neat. Okay. There is some mechanistic details behind that we're highly glossing over. Okay. But I would argue isn't worth the time to spend on. Okay. So what we're trying to do is address the key characteristic differences between it. Ketone versus our carboxylic acid. Okay. We don't have enolizable hydrogens in the carboxylic acid. So what we do is convert the carboxylic acid into an acyl chloride, the acyl or bromide, acyl halide ultimately. In the acyl halide form, we do have enolizable hydrogens. We now have the enol. We can now run the equivalent of our haloform reaction to do the substitution, hydrogen for bromine, because we're using Br2. We then follow that up with water to undo the acyl halide formation. Make sense? So each and every single one of these reagents is useful in driving this reaction. Yep.
You always have to do a lower halide. Sorry, that's probably not that clear. Like
No.
If you were attaching like chlorine onto this, you
Yeah.
would have to use, instead of the bromine, you'd have to use either chlorine or fluorine.
So fluorine's a bad thing to put on because the ability to use fluorine as an electrophile is not so high because you would need a positive fluorine. How likely are you to get a positive fluorine?
Pretty unlikely.
It is the most electronegative element. It's not going to happen. So you're looking primarily at bromine and chlorine. I use them kind of interchangeably. If you look at your second edition textbook, they actually push this. PCl3 and Br2 is ultimately making, I believe, the bromide, the acyl bromide.
Because if you do PBr3 and Cl2, bromine, like you
Bromines,
get
yeah.
things where they kick each
I
other.
see what you're saying.
Like
Yes.
better leaving groups.
Yes.
So other substitutions happen.
You'll get other substitutions.
Like set it up.
How much would that matter?
Well, you get
Probably in
95%
the-
yield on this one, so
In the grand scheme of things, not that
that's
that big a deal because you end up putting on a leaving group in either case,
right.
which you could then
Well,
substitute it out.
Is that ever a thing that's gonna come up where you're like?
Is it going to be a thing that's going to come up? No.
Oh,
Okay. So, the basics behind it, your carboxylic acids, there you go, not enolizable. The acid halides are. Once they can enolate, then we can, or enolize, we should say, not enolate, because we don't form the enolate. We can do the substitution. Once we've done the substitution, now we can do the hydrolysis. Okay. Where this is ultimately more importantly used, not on that slide, is that once we have our final product, we can react this with something like NH3, okay? And this can do a substitution reaction. Why has that become important?
because then you get amino acids and that's how you get DNA.
If that bromine's not there and I instead put on an NH2, the NH2 is an amine. The OH is an acid. What I've just created is an amino acid. So it is super commonly used in the creation of synthetic amino acids for synthetic proteins. Okay. We would just have to select to make sure whatever this group was matched whatever amino acid we were trying to target. Okay. Is there an added complication to that? we delete everything. So all I'm asking is there something else that we should consider when looking at that structure, potentially making amino acids?
Acid-base chemistry inside the structure.
Acid-base chemistry will come into play, okay? Which I'm sure everybody's super excited about because we get that negative charge. This would be a 3 and a positive. Okay? So we do have what is known as a Zwitter ion. Zwitter or Zwit, I think, is twin. So twin ions in the same compound. What else becomes a concern for this structure? Which thankfully has really not haunted us much this semester.
It's really reactive. There's a lot of negative.
Stereo center.
We have a stereo center. Okay. Most of our amino acids, in fact, I think it's 19 of the 20, are chiral. So that if we were going to try and create a synthetic amino acid, we'd have to be very careful to ensure that we maintained the proper chirality around that center. Okay. In this case, we aren't addressing it, so don't stress about it. Okay. But that would be something we would need to take into consideration when looking at it. Make sense? Okay. So, aldols. Right? This was our nice big summary of our aldols. We start with an aldehyde, strong base environment. We can deprotonate those hydrogens. We now have a nucleophile that can go through and react. Okay? Why bring the aldols back up? Sort of. We aren't going to use them necessarily. This reaction hinged on the reactivity of this hydrogen. That hydrogen is acidic because why?
The electron withdrawing effect of the oxygen.
Okay. That resonance effect in there. That hydrogen we could actually refer to or give it a name. We could call it what?
Alpha hydrogen?
Yeah, alpha hydrogen's fair. Which I may have entirely misspelled. We actually talked about it with the last reaction. Carboxylic acids don't have them, but the acyl chloride does.
Enolizable.
It's an enolizable hydrogen. Okay. Because I have that enolizable hydrogen, I can make that nucleophile. The aldol reaction can run. Okay. So why bring that up? Well, what if instead of having an aldehyde, I started with a carboxylic acid?
Not enolizable.
They aren't enolizable. So cool. Carboxylic acids don't have to worry about aldol reactions. What if I switch it to a chloride? Now it is enolizable. I could potentially see something go on with it. What if I switch it to an ester? Why not enolizable?
Resonance effect.
Okay, that resonance effect of that oxygen prevents that process. Okay, so we would say, really, all I got to worry about is the acyl chlorides. Okay, maybe the anhydrides if we wanted to push into that, but I don't have to worry about the esters or the acids doing aldol type chemistry. Okay, because you're writing something that makes me nervous. Because you shouldn't be writing that. We go through and we make that statement, and then someone runs a reaction, and what happens? It does happen, which then means they get to name it. Yes?
What happens if you put a NH2 instead of the OR?
You're running into similar issues. I'm going to bet that nitrogen does a better job doing resonance stabilization and prevents it from being enolizable.
More positive or more positive.
Yeah. Though that one I haven't seen, so maybe you should do real quickly some amide stuff so you can attach your name to it.
The teal reaction?
Yeah. Okay. So if we go through and switch this up, we take a strong base. Okay. Notice here, reflux for 4 hours. That's a long time. Okay, so this is not just let's just run it. We did an aldol reaction and a Michael reaction. Okay, admittedly, that's a bad example because that took all week. But those reactions tend to happen fairly easy. Okay, but we're refluxing for 4 hours. Okay, so we're giving this a lot of time. What we just discussed would suggest that there is no enolizable hydrogen, and it should therefore do what? Nothing. Okay? But we just said this gets a name. The name it gets, Claisen. Okay? So something does happen. Attempt it. Okay? You want me to go through the nucleophile part of it?
This
Yeah?
sounds super brutal being this 4 hours long, so
Yeah.
maybe not so much.
So our base, we've got a nice strong base up here, right? OCH2CH3. So there's our nice negative base. We want to remove our alpha hydrogen. That alpha hydrogen is removable because why?
We're heating it.
Yes, push it a little bit further. Why might it be enolizable if we looked at that drawing? Right? Because we're saying there's a resonance effect. Okay? And what we just discussed with the Hell-Volhard-Zelinsky is that it shouldn't happen because that resonance of the counter resonance from our other oxygen should prevent that from happening. Right? Okay, but we're now forced into the situation where, crap, it does. So it does happen. One of the questions that'll come up is why, okay? And that we'd have to see the full process to go through, okay? But really what I want you to be able to start with is that what we now have is our active nucleophile, okay? That active nucleophile is at that alpha position. If I have a nucleophile, what do I need to find now? Where's the electrophile? In the aldol, we made a nucleophile. Where was the electrophile? Another of the same material, which means what should I draw next to this?
The same. What's the starting material?
The starting material. Where's the electrophile in that structure? The carbonyl carbon. Initiate, run your reaction, see what you come up with for a product. Okay? And we'll talk through it and look at the details in just a little bit. But I want to see what you guys... Overall, very good. Okay? So let's take a look at these pieces. We've got reds, purples, and blues. The blue we said was what? The electrophile. Okay. What I also want to address is a black structure because somebody else came up with the idea of showing that. So we'll throw that in there also. Okay. Let's take a look at the red versus the purple. What is their relationship? They are resonance structures. So they are one and the same. Okay. Which resonance structure should you be using for your reaction? To make that decision, you have to decide which one is best and not use that one. So which of those two is the best resonance structure? The purple one's the best resonance. Why is the purple one the best resonance?
Your negative is on a more electronegative.
They're both unstable because of a negative charge. The purple one is better because you're putting the negative charge on the more electronegative element. So the purple one is a fantastic Lewis structure. Good job. Don't use it. Because when we're talking about reactivity, we want to use the first worst resonance structure. Okay? Second best. The second best is the red one. That's where my chemistry is. That carbon is now a nucleophile. Okay? Or, what else could that act as?
The base.
A base. Okay? What is the role of the black structure?
Solvent.
It is ultimately our solvent. But as was potentially pointed out, because I think I saw it, though I'm not positive, that solvent also has the ability to do what?
Donated by electron.
supply positive hydrogens, which means that base characteristic could react with that, and what happens? You kill the nucleophile, you revert backwards. I would argue that very first step of making the nucleophile, highly unfavored. Okay? You're forming a negative charge that is not nicely resonance stabilized because the ester's contributing in there. That step is insanely slow. Okay? Once it forms, it is so basic that what might it do? Pick up a proton from the most likely thing found, the solvent, and reverse the reaction. Right? So that formation of the nucleophile is not a good one. Okay? It is fine to show it react with the hydrogen, but you need to recognize that what that does is take you backwards. Okay? The same thing that makes the aldols tricky makes the Claisens tricky, in that you're reacting it with a second of the original material. Okay? So it becomes implied that you're allowed to do this. We're breaking the pi bond. The electrons go up to the oxygen. And we'd be making a really long structure that I'm probably going to run out of space for. But I'm going to try and do it anyway. New purple bond. O minus CH3 O. Yeah? Okay. What reaction did you just run? Okay, this was an addition reaction because you broke a pi bond. Okay, what did you break that pi bond with? A nucleophile. So that would be a nucleophile addition. That was unit 2. Okay? Which means this isn't new chemistry. To be new, we have to do something else with it. Okay? That's something else. A couple people were like, oh, well, we could protonate with the solvent. That's cool, you can do that. All you've really done then is a nucleophilic addition. Acid-base things aren't new steps. Okay? What structure did you just form? What functional group?
Tetrahedral intermediate.
It is a tetrahedral intermediate. Okay? Using that term as a red flag to do the next step of the mechanism. What else is it? It is a carbon connected to an OH, and that same carbon connected to the oxygen of an ether. You have a hemiacetal. And as we learned in the nucleophilic addition unit, last one, acetals are unstable. What do?
Revert back to the carbonyl.
They revert back to the carbonyl. So the electrons on our negative oxygen come back down to reform the pi bond. We would then need to eject a leaving group. What's our leaving group?
The blue ether.
So let's go with colors. Yeah. We want to eject the blue part. Okay. We could eject the red part, but that's actually ejecting to a higher energy thing. That's probably not a good thing. So we'd be ejecting that blue part. The result of that is that we now have the carbonyl reformed and we have our O negative. Yes? Okay. I got a lot of people stumbling on it. Well, but that's a bad leaving group. Look at the environment you're in. The environment you're in is a bad leaving group. On top of which, we can take it a step more than that. The leaving group is what?
Exactly.
Negative oxygen, CH2, CH3. It's literally the exact thing that we started in. Okay? So it's not a question of it being a bad leaving group. You're going right back to where you started. Okay? But at the same time, you formed a new structure. Okay? Everything about this doesn't lead to something more stable. We don't have conjugation here, so there's no reason to attach those two to each other. We don't form a more stable negative. which means through the course of the formation of this product, this is not a favored thing to do, which means this reaction sucks. Okay? If it sucks, Claisen doesn't get to attach his name to it. So it doesn't suck. What's special about this product? There are 2 carbonyls. 2 carbonyls on their own aren't that big a deal.
Doesn't have any charges.
It doesn't have any charges. I didn't start with any charges. In our mechanism up to this point, have we addressed the presence of H3O+?
No.
Why the hell is H3O+ added if that's where I end? There's nothing negative in that structure to react with the H+. Say, well, it's to neutralize the base that we started with. We've never done that before. Okay? When we're doing a second step, that second step is to fix our product, not to fix the random crap we have left over.
In this case, if we didn't fix it, it would react again.
Oh, do you have acidic hydrogens?
Do we have acidic hydrogens in our product?
Yes.
Yes. Where are those acidic hydrogens?
In between the 2 carbons.
In the middle. Those hydrogens are actually more acidic than our starting material. Much more acidic because I can just do resonance to the ketone as opposed to a resonance with the ester. This is a diketone extremely acidic structure, or dicarbonyl, I should say. Extremely acidic. What did we just eject as a leaving group?
Base.
A strong base. In the presence of a fairly acidic compound is going to do what? It's going to deprotonate it. Okay? So now what happens?
You replace those proteins.
We would have a negative charge in our structure. Negative charge could mean it's a base. It could mean it's a nucleophile. Could it run the reaction again?
Yes.
As a nucleophile, what might be an interesting characteristic of this?
It's huge.
It is huge. Take a look at our electrophile. How big is it around the electrophile?
It would be uncomfortable.
That's pretty uncomfortable. Which means steric hindrance prevents further reaction. This step is actually critical to the mechanism. I've now formed a more stable negative than I started with. This step is irreversible. Every other step is reversible, and if anything, favors the reactants. Because this last step exists, the equilibrium is slowly going to eventually shuttle everything across to this carbanion. But that's not our final product. How do I get our final product?
Add acid.
I add the acid. That's why the acid is there. It's this last step that is probably what gets Claisen his name attached to this, is recognizing that that last step is what's driving this reaction. Because otherwise we don't get a significant amount of product. Okay? The last step 2 is just an acid base. We put the hydrogen on there where the negative was. Okay? So, just like with the aldol, we can do crossed aldols, starting different aldehydes or different ketones. Guess what you can do with Claisens?
Same thing.
Same thing, different esters. Okay? Where'd it go? Oh, I remember. With the aldol, we had Aldol Condensations, right? There was always that condensation part of it. Okay? They call these Claisen condensations because we do form that pi bond. Okay? It keeps coming in and fading out. that hydrogen. If I don't have that second hydrogen to remove, the reaction doesn't happen. That second hydrogen is critical for the irreversible step. So if I look at a starting ester, so if we go all the way back up to the top, that starting ester had 3 hydrogens. But if I go through and make one of those a CH3, okay, do I still have 2 alpha hydrogens? I have the red and the blue. Yes, I do. So it could still potentially work. What if I make another CH3? Now the reaction doesn't work. Okay? You have to have 2 alpha hydrogens. The first one is to enolize so that we have the nucleophile. The second one is still technically an enolization so that we can get an irreversible acid-base step. So you have to have both of those hydrogens. In the case of the aldol, we just don't get the condensation if we don't have the second one. In the case of the Claisen, if we don't have the second one, we don't get it. We don't get a product at all. Okay? So it's a big kind of differentiation with our Claisens. Okay? I also want to kind of go through and reference something about the labeling. We've got these alpha-beta labelings coming in. We'll hear reference to alpha-beta carbonyl compounds or dicarbonyls. Okay, that's what they're referencing, is that proximity of the carbonyl. That becomes of critical importance to a mechanism known as the decarboxylation, which is a challenging process to go through, and ultimately you just have to have an alpha-beta keto ester. Alpha-beta, because of the positioning, keto, because you have a ketone, and ester, the other half has to start as an ester. Okay? If that happens, decarboxylation is fair game. If we don't have that proper alignment, decarboxylation doesn't happen. Right? Why I mention that? We'll look at the mechanism, not today, but we will look at that mechanism. Where I do... dang. Well, never mind. I thought I had a nice summary slide, just like we did with the aldol, but I don't see it. So we'll just go back over the complications on now next Wednesday. Okay?